Greetings of the day. I am Dr. Vineet, Assistant Professor in the Department of EEE. Today I will discuss some of the basic things about combinational circuits, and we will cover full adder and half adder in today's lecture. So as we all know that in digital electronics we have basically two kinds of circuits, combinational circuit and sequential circuit. So in case of combinational circuits, the output value will be depending on the present supplied input values, and it will not depend on any past input or output values. While in case of sequential circuits, the value of current output will be a function of past input and output values along with the current input values. So in combinational circuits, we mainly have uh, adder circuits, subtractor circuits, encoder, decoder, multiplexers, demultiplexers, and other important circuits like subtractor we have. So keeping in mind, basically in today's lecture we will cover half adder and full adder. So first we will start with half adder circuit. So half adder, it is a combinational circuit that is required to add two single bit binary numbers, right? So A and B are the two single bit binary numbers, and this half adder circuit will add these single bit binary numbers and it will produce two outputs. One will be sum and another will be C out, that is the carry output. So this half adder can be used only to add single bit binary numbers. There is no provision to add the third number or the incoming carry. So for LSB operation, suppose we have to add two 4-bit binary numbers, then for LSB this can be connected, this half adder can be connected, and later for the remaining bits we will be requiring full adders, because for remaining bits the carry may generate. So we will start the circuit with the truth table. First, in truth table we will explore all the values, all the possible values of inputs, and corresponding output values will be written here. So input combination for two input, total 4 combinations can be there. Either both can have 0 and 0, or A can have 0 and B can have 1, or B can have 1 and A can have 1 and B can have 0, or both can have 1. So corresponding output values also we will write here itself. So if we'll add 0 and 0, it will produce 0 as sum and there will not be any carry. So this will also be 0. If we'll add 0 plus 1, the sum will be 1 and carry will be 0. There is no carry generated in this operation. So output carry will be 0. Same way, 1 plus 0, 1 will be sum and carry output will be 0. Now if we'll add 1 plus 1, in that condition the sum will be 1 0. That is the binary equivalent, 2-bit binary equivalent of number 2. That is 1 plus 1, it is 2, and its binary equivalent will be 1 0. So this 0, that LSB will come here, it will serve as sum, and 1 will be the carry. So now we have completed the truth table for half adder circuit. Next we have to write the characteristic equations for this particular circuit. So two outputs are there. So for two outputs we will have two expressions, two Boolean expressions and two characteristic equations of this particular half adder circuit. So sum is the first output and it will be a function of inputs A and B, and we can write this in SOP form, sum of several minterms, and if you can see the minterms are 0 1 1 0, that is 1 and 2, and this expression can be written like this. Minterm can be represented like 0 1, that is A bar B, plus this one will be A B bar, and finally this sum since this expression, it is XOR operation between A and B, we can express it as A XOR B. So that will be one of the outputs that we have got here. Next, another output is carry output. So in carry output column, this column, we can see only one min term here. So simply we will write C out as a function of A and B inputs. It can be written as, that is third, it will be A dot B simply. Now C out, directly we can write it as A dot B. So both outputs we have obtained here, and we can use these output expressions, these characteristic equations, to construct the circuit for half adder. So first let us draw the input lines. This is A, this is B. Now using these lines, let us try to draw the circuit diagram. So for first, it is sum operation, it is XOR between A and B. A XOR B, that is nothing but sum. Next, for carry output, it should be an AND gate between A and B. A dot B equals to carry out. So this circuit actually represents a half adder circuit that is capable of adding two single bit binary numbers. But the demerit of this particular circuit is it cannot incorporate the carry generated from the previous bit operation. So for LSB operations, it can be utilized, but for further, when the carry will be generated and it has to be incorporated for operations, adding operations, then this cannot be used and we have to use the full adder circuit. So now we will start the full adder circuit. Full adder circuit has three inputs, which are A, B, and C in. A and B are the two single bit binary numbers that are to be added, and C in is the carry generated from the previous bit operation, and its outputs are same, sum and C out. The C out will be the carry generated in current operation. C in is the carry generated in the previous bit operation. So now this circuit has total 3 inputs and 2 outputs. So the truth table will have total, for 3 inputs, it will have total 8 combinations. So let us explore all the combinations here. So these 3 are the inputs, A, B, C in, and S and C out are the outputs. So all the combinations we will mention here. So one combination will be 0, 0, 0, another will be 0, 0, 1, another will be 0, 1, 0, another will be 0, 1, 1, another will be 1, 0, 0, another will be 1, 0, 1, 1, 1, 0, 1, 1, 1. So now we have written all the possible combinations for this particular circuit. All the possible input combinations we have written. Now let us add 0 plus 0 plus 0. So this operation, the first operation, will produce sum as 0 and C out will also be 0. There is no carry generated. 0 plus 0 plus 1, it will also not generate any carry and the sum will be 1. Same way, 0 plus 1 plus 0, it will also produce 1 and the carry generated will be 0. Now if we'll add 0 plus 1 plus 1, it will be equivalent to 1, 0. So that LSB will be 0, that will be sum, and it will be 1. the carry out will be 1. Next, 1 plus 0, the sum will be 1 and carry generated will be 0. Next, 1 plus 0 plus 1, again it is equivalent to 2, which is 1 0. So this LSB will come here 0 and 1 will be the carry generated for next bit operation. Next, 1 plus 1 plus 0, same thing, 0 will come here and 1 will come here. Next, 1 plus 1 plus 1, that is that will add to a binary equivalent, 2-bit binary equivalent of 1 1. So 1 will be the sum and 1 will be the carry. So now this truth table is completed, and next step is to identify the Boolean expression and to identify the min terms and to write the characteristic equations for both output values. So first we will start for sum output, and we will write this sum as an expression as a function of A, B and C in inputs, and it can be expressed as sum of several min terms, which are this one 0 0 1, that is 1, and corresponding is 0 1 0, that is 2. Then we have 4, and then we have 7. 1 2 4 7, that is for sum output. So if we will try to minimize this SOP expression using a K-map, it will be a 3-variable K-map. It will have 8 cells. This will be A. We can have B and C in here. Let us fill the K-map. So 1, 2, 4 and 7. 1, 2, 4, 7. As we can see here, it is not possible to group any of these min terms here, any of these implicants. We cannot group them. So we have to write this expression here. The complete expression we will write here, and we will see whether we are able to get this expression in some form where we will require the minimum number of logic gates. So first we will write the complete expression for sum. So 0 0 1, that will make it A bar B bar C in plus 0 1 0 A bar B C in bar plus 1 0 0 A B bar C in bar plus 7, that is 1 1 1, that is A B C in. So essentially, if we are using this expression, this characteristic equation to construct the circuit, we will be requiring total 4 3-input AND gates and 1 4-input OR gate will be required. Now let us try to write this expression in some other form. So we can take A bar as common in first two terms, and in bracket it will be B bar C in plus B C in bar, plus here we can take A as common, and in bracket it will be B bar C in bar plus B C in. So we know that this B bar C in plus B into C in bar, this is nothing but XOR operation between B and C in. So this we will write here, B XOR C in plus A B bar C bar in plus B into C in. This is XNOR operation between B and C in. Same thing we will write here. And now we can clearly see that this is nothing but an XOR operation between A and this term, B XOR with C in. So this expression can be directly written as A XOR with B XOR with C in. So finally the sum expression we have obtained here, it is So this will require a 3 input XOR gate to execute the sum operation. Now let us minimize the Cout expression. Let us first write the Cout expression in terms of the input variables. It can be written as summation of several minterms. So minterms are the number of ones in the output column. So again we will check here also we are having 4 minterms. So first one is 0, 1, 1, that is essentially 3. Then we have 1, 0, 1, that is 5. Then we have 1, 1, 0, that is 6. And then we have 7. These are the minterms for this particular thing. So first we will try to minimize using K-map. So let us fill the K-map with 3, 5, 6, 7. And now in this we can make several groups of minterms. So this will be one group of 2, this will be one group of 2, and this will be another group of 2. So with these 3 groups in K-map, the all variables, all minterms can be covered. So here the common term will be A into C in. In this group, the common is A and C in here. And here the common will be A into B. And this term, the common is B into C in. So finally, the minimal expression that we will be writing here, it will be A C in plus B C in plus AB. So this is what we have obtained here as Cout. So now we have got the both expressions, both characteristic equations for both output variables, sum and carry output generated. So now let us draw the final circuit for this full adder. This is input line A, this is input line B, this is input line C in. Now for sum output, we only need one 3 input XOR gate. So we will take A, we will take B, we will take C. A XOR B XOR C in. This will produce the sum output. Next, for Cout, we have total 3 product terms. So 3 AND gates will be required. So first we will take out A and we will multiply with C in. So one AND gate will be required here to execute this product term. So this will be essentially A into C in. Next, we have connected one more AND gate between B and C in. So this will produce B into C in. Finally, we need one more AND gate between A and B inputs. That is A, that is B, and one more AND gate will be producing this AB. And finally, these outputs, these AND gate outputs, they are required to be added, logically added. This logical addition will be performed by this particular OR gate. So this is the desired circuit for full adder. Now this full adder can be useful to add binary numbers having carry also. So it can add 3 bits in the input and it will produce sum and carry out. So this circuit is the desired circuit for full adder. So later In upcoming lectures, we will discuss half subtractor and full subtractor. Thank you.